Welcome back to the Deep Dive. Today we are heading on, well, what you might call the ultimate archaeological expedition.
I like that framing.
Yeah, it's a journey that spans billions of years. Our mission, really, is to try and uncover the earliest secrets of life. We're going to focus on the chemical, the planetary, and the experimental steps that took us from just non-living matter.
A pile of cosmic dust, essentially.
Exactly, from a pile of dust to the first organism. So today we are deep diving into what our sources call the astronomical nonsense that allowed life to take root here on Earth.
It is, without a doubt, the grandest puzzle science has ever faced. And I think before we even start looking at the evidence, we have to be really clear about what we're looking for.
What is life, right?
What is life? The sources are quite specific. Living matter isn't just a bag of organic chemicals, it's a complex molecular aggregate. And it has to have several key features that all work together.
Okay, like what?
First, it needs a management system, something to control its internal processes. And second, and this is absolutely critical, it needs a mechanism for transferring hereditary information.
The code. The blueprint?
The blueprint, precisely. But a perfect blueprint isn't enough, which is a point you raised earlier. If the system copies itself perfectly every time, it never changes. It stagnates.
So it needs to make mistakes.
Exactly. The third essential element is that the information transfer can't be perfect. There has to be what our sources call noise or interference. Errors have to creep into the copying process.
Mutations.
That's the engine of evolution. Without that capacity for mutation, you just have a very stable, very complex chemical machine. But you do not have life. Life is, by definition, a system that iterates and improves on itself.
So we're not just looking for a molecule. We're looking for a system that can manage itself, copy itself, and change over time. That immediately it highlights the sheer scale of what had to happen. I mean, we're starting with simple planetary stuff, and it has to go through this long, complex chemical evolution just to create the organic molecules, the bricks, as the sources call them.
It's the transition from geochemistry to biochemistry. And the real shock, the thing that anchors this entire deep dive, is when you just look next door, cosmically speaking.
At our neighbors.
At our neighbors. If the universe is made of the same stuff everywhere, why here? Why Earth? When you compare our planet to Venus or Mars, Earth's whole setup, its atmosphere, its geology, it's so wildly different that it genuinely qualifies as an astronomical miracle.
So let's start there. With that miracle, what made Earth so bizarrely different from the start?
To understand the miracle, you first have to understand what the default setting for a planet like ours should be.
Okay.
Our best theories on how solar systems form, the cosmogenic hypotheses, they all suggest that planets condense from this big, swirling cloud of gas and dust, the protoplanetary cloud.
Which means they should basically look like a small piece of the sun, chemically.
That's the starting point. Very, very rich in hydrogen. So the original primordial atmospheres, these planets, should have been full of simple hydrogen compounds.
So things like molecular hydrogen, H2.
H2, water, which is H2O, carbon dioxide, CO2, ammonia, NH3, and methane, CH4. And crucially, they should have been full of noble gases.
Like helium and neon.
Especially helium and neon. They're light, they're chemically inert, they should have been everywhere.
But if you look at our atmosphere today, you can barely find them. They're practically gone.
And that absence is our first huge clue. It's the smoking gun that tells us something catastrophic happened early in Earth's history. The fact that we have so little of these light noble gases compared to the sun means that Earth, very early on, lost its entire first atmosphere.
Just gone.
Gone. It just dissipated into space, probably stripped away by intense solar winds before the planet's gravity was strong enough or it had cooled down enough to hold on to it.
So what's left? I know we have argon, that's about 1% of our air.
We do, but that's the tell. It's overwhelmingly the isotope argon-40, and that matters.
Why that specific one?
Because argon-40 isn't primordial. It wasn't captured from that original cloud. It's radiogenic.
Meaning it comes from radioactive decay.
Precisely. It's continuously generated from the radioactive decay of potassium-40 in the Earth's crust and mantle. Its presence is a clear signal that what we're breathing is a secondary atmosphere. It's an atmosphere that degassed from the inside of the planet long after the first one was lost.
Okay, so this is where the comparison with our neighbors gets really interesting. The noble gases are like tracers, telling us about each planet's history.
Exactly. And this brings us to the fantastic data gathered by the Soviet Venera 11 and Venera 12 missions to Venus.
What do they find?
Well, they analyzed the argon isotopes, as we just said. Argon-40 comes from potassium decay, so you'd expect the amount to be related to the size of the planet. More rock, more decay.
Makes sense.
And it is. The absolute amount of argon-40 is pretty similar on Earth and Venus, and a bit less on Mars, which is smaller. That's the predictable part.
Okay, so what's the twist?
The twist comes when you look at the other isotope, argon-36.
That's the primordial one, the one from the original cloud.
That's the one. On Earth and Mars, argon-36 is almost gone. It's hundreds of times less abundant than argon-40. It confirms the theory we lost our first atmosphere.
And on Venus.
On Venus.
Yeah.
The abundance of argon-36 is equal to that of argon-40.
Wait, how is that possible? Venus is closer to the sun. It gets hit by stronger solar winds. Shouldn't it have lost more of its atmosphere than Earth?
It should have. That's what makes the data so incredible. The conclusion from scientists like M. N. Isakov was that Venus must have somehow skipped that massive atmospheric loss event that hit Earth and Mars.
It held on to its original air.
It seems to have captured its atmosphere directly from the protoplanetary cloud and somehow retained a huge chunk of it.
Well, Earth and Mars basically got a do-over.
They got a do-over. They have secondary atmospheres that bubbled up from inside the planet. And for the story of life, that's everything. Earth's slate was wiped clean, creating the possibility for a completely new atmosphere to form, one that life itself could eventually build.
And when you look at what life built, our modern atmosphere, that's where the term astronomical nonsense really hits home.
It really does. I mean, look at the comparison. Venus and Mars are the chemical default. Over 95% carbon dioxide. Mars has a tiny bit of free oxygen, about 0.2%. Venus has even less.
And Earth.
Earth is the opposite. CO2 is a trace gas for us, just 0.032%. And 21% of our air is free oxygen.
A chemically reactive, unstable gas.
It's chemically bizarre. Oxygen is a powerful oxidizing agent. It wants to react with everything. From a purely non-living chemical standpoint, an atmosphere with 21% free oxygen is fundamentally unstable. It shouldn't exist. It should have vanished by reacting with rocks and minerals ages ago.
So the fact that it's here at all is the miracle.
It is the miracle, and it's maintained only by the constant, relentless work of biology.
Okay, so if Earth was pumping out CO2 from volcanoes just like Venus and Mars, where did it all go? How did we get from that CO2 default to our oxygen anomaly?
Two critical processes, according to the sources. The first, and actually the more powerful one in terms of sheer volume, was chemical. It involved liquid water.
Water was the key.
Liquid water allowed for massive chemical reactions with surface rocks, weathering. This process essentially bound the atmospheric CO2 into carbonate rocks, locking it away in the crust for geological timescales.
So liquid water cleaned up most of the CO2.
Yes, but the second process is the one that's uniquely biological. Photosynthesis. This is the maintenance system. Plants take in CO2 and water, use sunlight for energy, and pump out free oxygen as a waste product.
Our air is basically biological exhaust.
It absolutely is, and it's in a constant state of dynamic equilibrium. The sources point out a mind-boggling calculation. If all plant life on Earth suddenly died.
If photosynthesis just stopped.
If it just stopped, all the free oxygen in our atmosphere would be gone in about 10,000 years. It would just react with the surface and disappear.
That's a geological blink of an eye.
It proves that life isn't just living on the planet. It's actively building and maintaining the planet's environment, holding it in a state that chemically should not exist. That is a cosmic scale consequence.
So understanding that oxygen is a product of life gives us a really important clue for dating when life started. The geological data says we had a relatively oxygen-rich atmosphere as early as 3.5 billion years ago.
And that's a huge piece of the timeline. It means life must have arisen, and not just arisen, but evolved the incredibly complex process of photosynthesis significantly before that. The oxygen is the effect, life is the cause.
And the oldest fossils we have.
The oldest known fossils are of blue-green algae, or cyanobacteria. They date back to between 3.5 and 3.8 billion years ago.
And these are not simple little blobs. They're already incredibly sophisticated organisms.
Exactly. They already have the full machinery for photosynthesis, a working genetic code, everything. They are highly evolved. So if these complex forms existed 3.8 billion years ago, the actual origin of life, that first fragile self-replicating system, must have happened much, much earlier.
How much earlier?
Probably in the first few 100 million years of Earth's existence. As soon as the planet cooled enough for liquid water to form, the process seems to have started.
That is an astonishingly fast start. Earth is 4.5 billion years old, and life got going within maybe the first half-billion years, which leaves
More than 4 billion years for biological evolution to do its work. The timescale is it's almost impossible to grasp. It's worth running through the major milestones our sources lay out.
Let's do it. For context, the universe itself is about 15 billion years old.
Right. Earth forms 4.5 billion years ago. Photosynthesis and the oxygen atmosphere get going, as we said, around 3.5 to 3.8 billion years ago. And what's really surprising is that's also when we think eukaryotic cells with a proper nucleus emerged.
So the biggest leap in cell complexity happened right at the beginning, alongside the oxygen revolution.
It seems so. But then evolution seems to slow down, or at least it changes focus. It spent a vast amount of time just tinkering with single-celled life.
How long are we talking?
We have to wait almost 2.5 billion more years until about 1 billion years ago for the first multicellular organisms to show up. And these were just soft-bodied, jelly-like things.
A billion years of just being multicellular bags of jelly? That's a long time.
It's an eternity. Then it took another 400 million years for the first organisms with skeletons to appear. That's the start of the Cambrian explosion, about 600 million years ago.
And life finally moving on to land.
That happens around 400 million years ago. So think about that. Everything you picture when you think of evolution, dinosaurs, forests, mammals, it's all crammed into the last 15% or so of Earth's history.
In us.
The first mammals appear after the big extinction, 65 million years ago. And humanity. Cro-Magnon man shows up just 40,000 years ago. A total blink of an eye.
The lesson here seems to be that getting the first system up and running was relatively quick. The evolution of that system took billions of years. But it's that initial jump from chemistry to a system that's the real mystery.
And that takes us right into the world of pre-biological chemistry.
The attempt to recreate that first step in the lab.
Exactly. This field was basically founded to bridge that gap. Scientists like Melvin Calvin, Stanley Miller, and Harold Urey wanted to see if they could get the building blocks of life to form spontaneously under the conditions of the early Earth.
And the most famous of these experiments is, of course, the Miller-Urey experiment.
It was a game changer. It took the origin of life out of the realm of philosophy and put it squarely into laboratory science.
So what do?
They created a model of the primitive atmosphere, a mix of methane, hydrogen, ammonia, and water vapor. They circulated this gas mixture in a closed, sterile glass loop and zapped it with high-energy electric discharges.
Simulating lightning.
Simulating lightning. And when they analyzed the water that condensed out of the system, they were stunned.
What did they find?
A whole variety of organic compounds had formed, including, critically, several amino acids like glycine and alanine, the basic components of proteins. It proved that the bricks of life could form easily and naturally.
So lightning was one possible energy source. But the sources say that the biggest source of energy on the early Earth was probably UV radiation.
By far.
Yeah.
The primitive atmosphere was non-oxidized, which means it had no ozone layer.
Nothing to block the sun's UV rays.
Nothing. So the full spectrum of solar UV radiation just hammered the planet's surface. On top of that, you had shock waves from meteor impacts, heat from volcanoes, radioactive decay. There were many energy sources.
But you've made the point that it's not just about how much energy there is, it's about how useful it is.
That's a crucial distinction. The total amount of energy is less important than what the sources call the coefficient of performance. How efficient is a given energy source at driving the specific chemical reactions you need to make life's building blocks?
And to build those complex blocks, you first need some simpler intermediate products. What were the key ones?
It really boils down to two main intermediates: formaldehyde and hydrogen cyanide, or HCN. These formed easily in the gas phase from the simpler stuff, and then they dissolved in the early oceans. And it's in the water that the really interesting chemistry happens.
So how do you get from formaldehyde and HCN to, say, an amino acid?
There's a very efficient pathway called the Strucker synthesis. It's a natural reaction. You mix ammonia, formaldehyde, and HCN in water, and they react to form intermediates.
I'm not going to pretend I remember the names.
Amine, nitriles, and cyanohydrins. The names don't matter. What matters is that these then react with water, they hydrolyze, and boom, you get amino acids. It's a very straightforward, robust process.
So HCN is a key structural piece. Was it also important for making the parts of DNA and RNA?
Absolutely central. And this is where the chemistry gets almost spookily elegant. Take adenine, one of the 4 letters of the genetic code.
A, T, C, G. So the A.
The A. The entire complex structure of adenine can be formed by the self-assembly of just 5 molecules of hydrogen cyanide.
Just 5 HCN molecules snapped together to make it.
They snap together to make adenine. It's an incredible piece of chemical economy. You don't need a dozen different precursors. You just need a lot of HCN in the right conditions.
Wow. Okay, so that's amino acids and nucleic acid bases.
Hmm.
What about the third major piece, the sugars? Like ribose for RNA's backbone.
For sugars, the key ingredient is formaldehyde. They form through a process called alkali condensation of formaldehyde.
Which means you need a basic alkaline solution.
Exactly, and you need a catalyst. Experiments by scientists like Gable and Panaparuma showed that common clay, like kaolinite, works as a fantastic natural catalyst.
So clay lagoons.
Clay lagoons, or anywhere with wet clay and formaldehyde. They took formaldehyde solutions, used kaolinite as a catalyst, and they produced a whole range of sugars. Trioses, tetroses, pentoses, and most importantly, they produced ribose, the exact sugar needed for RNA.
So all the pieces are falling into place. We've got the components for proteins, for DNA and RNA bases, and for the sugar backbone. What about the really complex stuff, like the machinery for energy, like chlorophyll?
Those are based on structures called porphyrins.
Yeah.
They are absolutely vital. They're the basis of chlorophyll and also key parts of enzymes that protect the cell. And yes, experiments showed that porphyrins could also be synthesized abiotically by zapping a mixture of methane, ammonia, and water with an electric discharge. Same basic setup as Miller-Urey. It showed that even these incredibly elaborate molecules were accessible through simple, non-biological chemistry.
So all the individual bricks are on the table. The next challenge is linking them together, making the polymers, the long chains like proteins and nucleic acids.
And this is a harder step. It requires more energy, and it often involves dehydration, removing a water molecule to form a bond. That's tricky to do in an ocean full of water.
So how was it done?
A scientist named Schramm managed to synthesize polynucleotides chains of nucleic acids by using powerful coupling agents called metaphosphoric esters, or MPEs.
And they forced the links.
They forced the links. He produced real polynucleotides of various lengths, but there was a critical catch. The sequence of the bases in these chains was completely random. He had made the polymer, but he hadn't written a message.
And for proteins?
Sidney Fox showed that you could do it with heat. If you take a dry mixture of amino acids and just heat them up, the water is driven off and they link up into long protein-like chains he called proteinoids.
So the takeaway from all of this experimental work is pretty powerful.
It's a huge conclusion. It demonstrates that all the major classes of biologically important molecules could, and very likely did, form non-biologically under the conditions of the primitive Earth. The soup was ready.
But having all the ingredients doesn't mean you have a meal. You have this major challenge of destruction.
It's a huge problem. The molecules don't just have to form, they have to accumulate. They have to reach a high enough concentration for the next steps to happen.
And the very same UV radiation that was helping to create them was also incredibly effective at destroying them.
Especially the longer wavelengths. With no ozone shield, the destruction rate on the surface should have been immense. It's hard to see how anything complex could have survived for long, so we need a safe harbor.
And the obvious one is the ocean.
The ocean. Depth protection. If compounds were synthesized near the surface, they could get transported down by convection or just by dissolving, down to depths where the destructive UV couldn't reach them. Water is a great UV shield.
So, assuming this process of create and protect went on for a very long time, how concentrated could this primordial broth have become?
That's a question Carl Sagan famously tried to answer. He did a calculation. He assumed the process went on for about 1 billion years without significant destruction.
And what did he find?
He estimated that several kilograms of organic compounds could have formed over every single square centimeter of the Earth's surface.
That's an enormous amount of stuff. What does that translate to for the ocean's concentration?
If you dissolve all of that in the early ocean, it would create about a 1% solution of organic compounds.
And is that a lot?
It's a huge amount. It's about 10,000 times more concentrated than the nutrient level in modern seawater. Our sources call it a fairly strong nutrient broth. It's dense enough that the next stages of organization become plausible.
Okay, so that's the global broth theory. A slow accumulation over the whole planet. But what about the idea that life started much faster in some kind of local hotspot?
Right, because even a 1% solution might not be concentrated enough for the really complex polymer building to happen efficiently. So the focus shifts to specific locations where the conditions were just right.
And the first major candidate is underwater volcanoes.
Mukin's model. It's a fantastic natural chemical reactor. You have intense heat, high pressure, and a constant supply of the simple ingredients coming right from the Earth's mantle: methane, ammonia, hydrogen sulfide, CO.
And it solves multiple problems at once.
It does. The heat and pressure speed up the creation of precursors like HCN. The deep ocean water provides a stable environment and, critically, a rapid cooling factor, which saves the new molecules from breaking down. And all the ash and mineral grains thrown out by the volcano.
They act as catalysts, surfaces for the reactions to happen on.
Exactly. They concentrate the molecules and speed up polymerization. It's a self-contained, high-yield factory, completely shielded from the UV radiation on the surface.
Plus, it doesn't need to assume that the whole planet had a methane-ammonia atmosphere. The volcano provides its own local chemistry.
A very important point. The sources even run the numbers. They suggest that strong eruptions could produce up to 10 to the 17 grams of organic compounds per year. It's a massive, focused source of production.
Okay, what's the second big hypothesis? The clay lagoons.
Bernal's hypothesis. The idea that life started in the sludge of small, drying lagoons. Here, the catalyst isn't volcanic heat, it's the clay particles themselves.
I mentioned them with the sugar synthesis.
Right. The layered structure of clay minerals is perfect for absorbing small molecules from the water, concentrating them, and holding them in just the right orientation to link up into long chains. It's a template for polymerization.
So whether it's deep-sea vents or shallow lagoons, a really fascinating idea emerges here, which is that natural selection was happening before life even existed.
A kind of chemical natural selection. It was observed that some of the more complex organic molecules are just physically more stable. They're more resistant to being destroyed by heat or UV light than the simpler ones.
So over time, the tough ones stick around.
Exactly. The more complex, robust molecules would naturally survive and accumulate just because they were harder to break. It's a form of selection built into the physics and chemistry of the system itself, well before biology comes into the picture.
Okay, so we have a concentrated broth, we have the polymers, now we get to the final and most difficult qualitative leap: organization.
Right. Once you have polymers, especially proteins, in this broth, they would naturally start to clump together into what are called coacervate drops.
What are those exactly?
Think of them as tiny, concentrated bubbles of molecules. They spontaneously separate out from the surrounding water, like oil from vinegar. And they act like little sponges, sucking up and concentrating all the protein molecules inside their boundary.
And this is the basis of Opren's famous hypothesis, that these coacervates were the precursors to living cells.
Opren's insight was that these drops, even though they weren't alive, showed a kind of basic metabolism. They had boundary, and they could absorb substances from the solution, run chemical reactions inside, and release waste products. There was a flow of matter and energy.
And they also showed that chemical selection we were just talking about.
Yes. Opren argued that there would be a natural selection of these drops, the ones where the internal chemistry was more stable, where the rate of building things up was faster than the rate of things breaking down, would achieve dynamic stability. They would last longer.
The well-organized drops survived. The messy ones dissolved.
Precisely. It seems like a perfect bridge to life. They have a boundary, metabolism, and selection, so why isn't it the final answer?
What's the fatal flaw?
They are missing the one single non-negotiable attribute of life. They have no copying system, no code, no way to pass on their specific successful structure to offspring. They can't reproduce based on a blueprint.
It's all just random chemistry inside the drop.
It is, and the sources are very clear on this critique. Having all the building blocks doesn't explain how an automated factory capable of self-reproduction arose.
And that factory's control system is just unbelievably complex.
It's phenomenal. All the instructions are stored in the one-dimensional sequence of DNA written in a 4-letter alphabet. And that code is then translated into the 20-letter alphabet of amino acids to build all the protein machinery. The question is, how did that precise interlinked system just appear?
Which brings us to the great paradox, the chicken and egg problem of biology.
It's a brutal paradox. Modern DNA, the master blueprint, is completely helpless on its own. It can't copy itself, it can't repair itself, it can't even be read without a whole team of complex protein enzymes.
But those enzymes can only be built if the DNA tells the cell how to build them.
You need the DNA to make the proteins, and you need the proteins to read and copy the DNA. So which came first?
If you assume they both just appeared at the same time by pure chance.
The odds are astronomical. The sources equate it to believing in miracles. It's like a monkey at a typewriter randomly banging out Shakespeare's 66th sonnet, letter perfect, by pure chance. The probability is effectively zero.
So that forces the conclusion that this whole replication system must have evolved step by step from something much, much simpler.
Exactly. And that sent researchers searching for an intermediate molecule, something that could do both jobs, be both the blueprint and the machine.
And that's where RNA comes in, the RNA world hypothesis.
Yes. Based on the work of people like Alexander Rich, they pointed out how structurally similar DNA and RNA are, and then came the key discovery. Some very simple viruses, like the tobacco mosaic virus.
They don't have DNA.
They don't. They only have the simpler RNA molecule. And in those viruses, RNA does both jobs. It carries the genetic information, the code, and it also helps catalyze the synthesis of proteins. It's both the chicken and the egg.
It's the bridge.
It's the logical bridge. The hypothesis is that both DNA and our modern protein synthesis system evolved from an earlier, simpler world where a protonucleic acid, something like RNA, ran the whole show. It could have formed the first living systems, solving that paradox of needing proteins to get started.
So even if life did manage this incredible leap, it still had to survive on a very hostile planet.
Yeah.
Let's go back to that UV radiation. We said it was a good energy source, but it's also a killer.
It was the #1 environmental threat. Other radiation sources, like cosmic rays or natural radioactivity from the Earth's rocks, they weren't the main problem. The radioactivity was maybe 10 times higher than today, but manageable.
The sun was the real danger.
The sun was the constant existential threat. The atmosphere was transparent to the most destructive wavelengths of UV light, and a simple early life form would have been incredibly vulnerable.
Can we put a number on that? How bad was it?
The sources quantify it pretty starkly. The UV flux at the surface was about 5,000 ergs per square centimeter per second. Now, if you estimate a dangerous dose for a primitive organism at, say, 1,000 ergs per square centimeter per generation, and a generation might have been just minutes or hours.
The actual radiation was way, way too high.
It was 5 million times too high for survival on the surface. This isn't a small problem. It's a hard physical constraint. There is no way life could have started on the surface of the Earth.
So that leads to only one possible conclusion.
The Deepwater Sanctuary. It's the only viable solution. Life could only have formed and developed at a significant depth underwater, where the water column could act as armor. Just a few tens of meters of water would reduce that lethal UV flux by tens of millions of times.
So life was born in the dark.
It was born and evolved in the deep, only coming to the surface much later after it had produced enough oxygen to build its own shield, the ozone layer.
Beyond the environment, there's another deep internal mystery that just seems to defy all statistics, and that's the puzzle of chirality.
Ah, molecular handedness. This is maybe the most elegant and deeply weird problem in the whole story.
So explain what it is.
Many organic molecules, including amino acids and sugars, can exist in two forms that are mirror images of each other, like your left and your right hand. They're chemically identical, but they're not superimposable.
And when you make these in a lab, you always get a 50-50 mix of both left and right-handed versions.
Always. Because chemically, there's no preference. It's random. And yet, when you look at life,
It's not random at all.
it's completely biased. All proteins and every living thing on this planet are built exclusively from left-handed amino acids, and the sugars are overwhelmingly right-handed. Life uses only half of the available molecules.
Why? It's not like the right-handed amino acids wouldn't work?
They would work fine chemically if you build a whole system out of them, but you can't mix and match. The moment the first successful replicating system picked one-handedness, all subsequent evolution was locked into that choice. Trying to stick a right-handed amino acid into a left-handed protein is like trying to fit a right-hand glove on your left hand. It just breaks the whole structure.
So were there any plausible theories for why that initial choice was made?
Pastors thought there must be some asymmetric force in nature. There were experiments with circularly polarized light, which can preferentially destroy one version over the other, but there's not a lot of that kind of light coming from the sun.
What about crystals?
Bernal suggested that maybe the molecules formed on the surface of an optically active crystal, like quartz. The problem is, quartz crystals in nature exist in both right and left-handed forms in equal amounts. So that just pushes the question back one step. Why was one type of crystal chosen over the other everywhere on Earth?
So the bottom line is,
We have no idea. The reason for the singular asymmetry of all living matter remains a complete and total mystery.
which brings us to a question that I think a lot of people have. If life could start spontaneously billions of years ago, why isn't it happening right now? Why don't we see new life forms popping up in puddles?
It's a great question, and the sources give two main reasons. The first is competition.
Anything new would just get eaten.
Immediately, any fragile little protocell or complex polymer trying to get started would be an instant meal for the hyper-efficient, highly evolved bacteria and viruses that already occupy every single niche on the planet. The soup is gone because life ate it.
So existing life prevents new life from starting. What's the second reason?
Probability. It's possible that the initial genesis of life was a ridiculously improbable event. A fluke that happened just once, under a very specific set of early Earth conditions, the right chemicals, the right temperature, the anoxic atmosphere, that just don't exist anymore.
A unique moment in time.
A unique moment in time. And there's one last little mystery tied to that. We know that all living proteins are built from a standard set of 20 amino acids.
But the Miller-Urey experiments produced more than that.
Way more. Over 100 different amino acids are known to exist or could form abiotically. Yet life settled on a specific palette of just 20. Why those 20? That selection is deeply tied into the origin of the genetic code itself, and we still don't know why that specific set was chosen.
So we've journeyed through cosmic history. We've mixed chemical cocktails in the lab. We've understood the vastness of the timeline. We've shown that all the bricks could form. But that final step, the mechanism for creating the code for replication, that remains the ultimate black box.
It really does, and it brings you back to a place of real scientific humility. Francis Crick, who co-discovered DNA structure, said it best in 1971. He said, "We do not see a path from the primary broth to natural selection. One may conclude that the origin of life is a miracle, but this only testifies to our ignorance."
So here's the final provocative thought we want to leave you with. Let's combine that replication paradox with the mystery of molecular handedness. Given the astronomical odds against the genetic machinery just randomly assembling itself, and the fact that all of life is built with only left-handed blocks, the question isn't just how the first cell organized itself.
The deeper question is why.
Why did it choose only 20 molecules out of hundreds? And why did it decide to completely ignore half of the available symmetrical universe of molecules? Is there some undiscovered law of physics that pushes matter in that direction? Or was the first instance of life just a single random choice? A cosmic coin flip that landed on left, and the entire biological universe has been forced to obey that one ancient decision ever since.
Something to mull over until our next deep dive.
Until then, keep digging.